This video is about the Copenhagen interpretation and why it is the only game in town. So what is the Copenhagen interpretation? Copenhagen is poorly taught in universities, if at all. One well-known commentator says about Copenhagen, the electron is like a wave when you're not looking at it, and like a particle when you are. He then goes on to say that's the state of the art for Copenhagen even today. Such a glib and willfully ignorant statement is of course wrong. If you've been taught that version of Copenhagen, you've been taught a seriously novel version where all the philosophical underpinnings have been stripped out. So again, what is Copenhagen? Copenhagen is actually a family of interpretations. Why? The founders of Copenhagen, Bohr, Heisenberg, Born, etc., did not always agree on everything. And they certainly did not sit down together and write out exactly what the Copenhagen is. Rather, Copenhagen is the interpretation that evolved over time at Bohr's Institute for Theoretical Physics in Copenhagen during the 1920s. Copenhagen was originally linked to positivist philosophy and verification, but it's probably fair to say that a more modern variant would probably directly reference the original Kantian philosophy and Popper's falsification. Positivism is a derivative of Kantian philosophy around in the 1920s, probably out of fashion now. I wouldn't necessarily encourage anyone to dive deep into philosophy just to clarify the difference between the two approaches, as that can be seriously hard work. Hopefully this presentation will cover those features relevant to quantum physics. So again, what is Copenhagen? We start with this man, Immanuel Kant, a German philosopher. Kant said, "We know the world through our senses, and from that information construct mental models to understand and predict interactions with the external world." The Kantian view can be represented by the following diagram. The left-hand side represents the external world. Only that part of the external world which interacts with a person's senses is observable. The rest of the universe is utterly unknowable. The senses sit on the boundary between the person's self and the external universe. The self contains the mental models used to understand the universe. The Copenhagen worldview, primarily created by Bohr, but based on the work of Kant, can be represented by this diagram. Similarity is not accidental. Senses are replaced by measuring devices. Consciousness is replaced by intelligence. Could be a robot, for example. And self is replaced by an observer. In Copenhagen, measurements are objective elements of reality, to use Einstein's terminology. That is, they are real. The waveform is not, is a mental construct. Schrödinger's cat, for example, does not represent an issue for Copenhagen. Its measured state is simply unknown. The measurement simply hasn't been done. The waveform represents a cat which is half alive and half dead. But that's okay, because it's not a real thing and represents our knowledge of the cat, which is a 50% chance of being alive and a 50% chance of being dead. Instantaneous collapse of the waveform also does not present an issue, since the waveform is not real and so is not subject to any relativistic constraints. In fact, most quantum paradoxes are the result of assuming the waveform to be an element of reality. The philosopher Karl Popper claimed to be scientific, a theory had to be falsifiable. That is, it had to be testable against the real world and potentially shown to be false. If it's not falsifiable, it's not a scientific theory. That sounds like common sense, but a lot of modern physics is replete with stuff that is not falsifiable or ever likely to be. Examples include multiple universes, microscopic wormholes connecting particles, particle trajectories, and the granddaddy of fantasy physics, string theory. So why are these theories still around? If you want my view on that, refer to the first video in this series. One thing is certain. Abandonment of falsifications led to a position where physicists seem to believe they can choose whatever interpretation they feel like. However, physics is not primary school. Not everyone gets a prize. Not all theories are the same. Copenhagen says that we can only probe the universe by making measurements. So the obvious question is, what is a measurement? A measurement can range from a particle interaction, for example, an electron bouncing off an atom, to giant machines similar to those in CERN. Most important thing is the interaction provides information about the measured system. Bohr believed that measurement is essentially classical. It's possibly okay when we deal with position, momentum and charge, although it requires Newtonian mechanics to be developed before we can fully understand quantum mechanics, supposedly more fundamental. It becomes harder to justify when we look at things like spin, and definitely problematic when you talk about something like quark color. We take a slightly different view to Bohr and call the resulting interpretation the ticker tape interpretation to avoid any confusion. Just to reiterate, ticker tape interpretation is part of the family of Copenhagen interpretations. As such, it takes over the Kantian worldview. In addition, all measurements are recorded to a metaphorical ticker tape, hence the name. In our analysis, we use the simplest possible measuring devices, called Mach devices, or simply M devices. They have the following properties. 1. The result of a measurement is a real number or a range of real numbers. Why? Real numbers are completely ordered. If we have one measurement over here and another over here, it's possible to compare the two and say which is the greater. 2. Mach devices are black boxes. The internal workings are completely hidden from us. We don't want to know how the devices work. Our theory should work for all measuring devices, not just some specific cases. 3. Measurements are repeatable. Repeatability is at the heart of measurement, but it's actually quite a subtle concept. If a specific device can only be used once, for example a photographic plate, repeatability means that devices of that construction must behave in the same way. 4. Measuring devices do not include a clock. Measurements arrive without a timestamp. The measurement of time involves a separate device, a clock. Some issues immediately present themselves. Measurements can change over time. For example, position. If two measurements are made with a device and they differ, does that mean the measuring device is not working? Or perhaps it's not a measuring device. Or perhaps differing measurements are okay. To avoid this issue, we adopt the following strategy. 1. We stick to stable systems. That is, systems where properties which are repeatedly measured give the same results. We develop our quantum theory in such a case. 2. We make a clock and add timestamps to the measurements as they arrive at the ticker tape. 3. We expand our theory to cover values that change over time. Until further notice, our discussion will be about stable systems. Another issue. Suppose we have two measuring devices, X and Y, which purport to measure the same quantity. The results of X and Y are plotted and are not the same. Which device is correct? Which contains error? Do they both contain error? It's not possible to tell. This is called a calibration problem, but the real issue is, how do we know what we're measuring? There is an argument that if the output of devices is deterministic, it is not possible to determine what they measure from an examination of measurement outputs alone. So how do we know what we're measuring? Fortunately, there is a solution. We say devices are conjugate and measure conjugate quantities if a measurement, one quantity, destroys information about the other. A system of conjugate devices defines a quantum system, which are more commonly referred to as particles. In Copenhagen, particles are constructions, which incidentally strongly suggests that space-time is also a construction, but I digress. Particles are definitely not excitations of quantum fields. We claim that commutator relations define what the devices measure. For example, anyone who's done Quantum Mechanics 101 knows what these operators measure. Furthermore, commutator relations can be used to define a scale. If a measuring device is replaced by one that uses a different scale, even across the universe, then a change of scale will show up in the structure constants, or may do. Note that the uncertainty principle appears naturally out of our solution of the calibration problem. It is the randomness injected into the measurement stream by the conjugate measurements that allows us to understand what we are measuring. A few quick points. The diagram showing two measuring devices with error bars is misleading. Quantum measurements are always exact, since they are the only source of information. We call that the principle of exact measurement. Saying that, not all measuring devices are Mach devices, since the results of the measurements are not always repeatable. For example, a radar gun has perhaps a 3% error. If a sequence of measurements are made under identical circumstances, the results are not guaranteed to be the same. 3. Our solution to the calibration problem, namely using the commutator relations to define what we are measuring, shows that all measurement is relative. A single measurement stream on its own is meaningless. Hence the name Mach device or M device. A history is a possible sequence of measurements. That is a possible ticker tape. It is possible to establish a mapping from history to algebras, such as real numbers, complex numbers, quaternions and octernions. If history 1 maps to psi 1 and history 2 maps to psi 2, then the history corresponding to the combined history 1 and history 2, maps to psi 1 times psi 2. Similarly, history 1 or history 2 maps to psi 1 plus psi 2. Feynman's rules are specific examples of these mappings. Feynman provided very specific rules for assigning numbers to the interactions in space-time, which is the subject of another video. Feynman's diagrams represent possible histories, that events that could possibly happen. Virtual particles and interactions aren't real, just possibilities. If you apply the same approach to a coin toss, the possible history would consist of a head and a tail. Or applying the approach to Schrodinger's cat, possible histories would consist of a dead cat and a living cat. All living, of course, in their appropriate configuration spaces. The takeaway is that space is not a bubbling cauldron of particles popping in and out of existence. In Copenhagen, measurements are real. Particle and fields are constructions of the mind. Saying that, it is easy to be fooled. If a mental model is so good, it never or hardly ever is wrong, then humans tend to accept it as real even though it's not. A classic example is our eyesight. It's tempting to believe that what we see is real, but in fact it's not the case. Everyone has a significant blind spot where their optic nerve enters the retina, but no one can see it. Your brain fills in the missing information with best guesses. What you see is a construct. It's in your head. There are enough other optical illusions, or should I call them paradoxes, to demonstrate that it is not real. But what happens if the mental model is perfect, which one day may be true in the case of quantum mechanics? Then the fields would have some sort of claim to reality, but they would still be constructions. Anyway, once the rules for combining histories are known, it's relatively easy to derive the full quantum formalism, but that's a topic for another video. What happens if we have two conjugate properties x and y? We measure x, then measure y, and then measure x again. We now know that the value of x has probably changed, but when was the value of x determined? There are two possibilities. One, the value of x was determined when the measurement of y disturbed the value of x. The new value was revealed when x was finally measured. Two, the second possibility, due to Bohr, is that the universe does not make up its mind what the value of x is until it's asked. This led Einstein to quip to Bohr, "Do you really believe the moon is not there when you're not looking at it?" The first common sense approach is called a hidden variable solution. The description of a particle after the measurement of y would need to include one or more hidden variables from which x could be derived. In 1935, Einstein, Podolsky and Rosen upped the ante by producing the so-called EPR paper, which discussed the measurement of properties of two entangled particles. Suppose that the measurement of A for the two particles must sum up to 0, perhaps a requirement arising from conservation of spin or similar. We measure the right-hand particle and find A equals -1. We now know if we measure the left-hand particle, we would get A equals 1. If Bohr was right and the universe only decided what value A had when it is measured, a spooky action at a distance instantly updated the left-hand particle so A equals 1. In the 1960s, John Bell produced his famous inequalities that any hidden variable theory would need to obey. Quantum mechanics did not obey them. Hidden variables could not explain EPR-like experiments. Einstein was wrong, Bohr was correct. Interestingly, the Nobel Prize in Physics for 2022 was awarded for experimentally showing the predictions of quantum mechanics were correct and the real world did not obey Bell's inequality. Did anyone really think that the most accurate physical theory ever was going to be wrong in this simple case? Anyway, the result of Bell's work is that those used to describe the measurement of conjugate properties as disturbing values has changed the language to say that the measurement of the conjugate properties destroys information about prior measurements and that associated values are no longer well defined. Quantum mechanics is really a theory about information. By the way, Einstein wasn't an advocate of hidden variable theories. Having a monster mind, his position was far more nuanced. At the time of EPR, von Neumann had already produced a no hidden variable theorem. The purpose of the EPR paper was to show how unreasonable and incomplete the authors thought quantum mechanics was. Now we have a quantum theory for stable systems. We introduce a clock that timestamps measurements as they arrive at the ticker tape. Once we have a clock, we can introduce Schrödinger's equation and the Hamiltonian. We now know how to do all of quantum physics, and gravity shows up in this framework via its effect on the clocks associated with each observer. This video is only a very superficial overview. Hopefully I will have convinced you that Copenhagen/ticker tape is the only game in town. Just to reiterate, 1. Copenhagen is based on simple ideas from Western philosophy that predate quantum mechanics. Ideas that have occurred to every drunken group of friends in a pub and are ultimately undeniable. It is at the heart of movies like The Matrix. 2. It accepts experimental results as is. It does what it says on the can. There is no need to introduce complex mathematics to model highly speculative underlying mechanisms like hidden extra dimensions or wormholes or multiple universes and other speculative nonsense that can be never demonstrated or tested. Why would you do that? 3. Copenhagen provides a clear justification for the uncertainty principle. It is simply part of our definition of a particle and our solution to the calibration problem. The uncertainty principle does not come from a Fourier analysis of waveforms or anything similar. Rather, waveforms have to comply with the uncertainty principle. 4. The formalism of modern quantum mechanics can be derived from first principles. Let's roll back to the original approach adopted by the early 20th century pioneers. They were pretty smart guys who thought pretty deeply about things. They basically got it right. If we don't, we risk wasting another 50 years of research in fundamental physics. If you feel you got something from this video, please like this video and subscribe to this channel. Please do it now so you don't forget. Thank you.